Okay, so now that we've talked about redox reactions for a couple of days and finished half reactions, we get to go over electrochemistry, which, as you're guessing, probably has something to do with chemistry causing electricity to happen or vice versa. We may talk about batteries, and we'll probably mention electro and also try to forget that this monstrosity ever took place. Electrochemistry is going to be exactly what the name says. It's the interplay between electricity and chemistry. So it may be chemical reactions causing or creating electricity, or the other way, electricity causing some kind of chemical reaction to take place. And we'll see it happen both ways. First day on Tuesday, we'll talk about voltaic cells here, where it's a spontaneous reaction, where chemical reactions cause electricity to happen. And the other time later in the week, we'll talk about the opposite, which is electrolytic cells, where now electricity is used to kind of jumpstart or trigger a chemical reaction that would not happen on its own. If you've ever seen anything that looks even remotely like this, you know what rust is. But why do some things rust and some things don't? Look at that. And today we're going to see how we can tell whether something will undergo oxidation reduction or whether it will not. We use table J to tell whether a redox reaction will happen and also which elements will be oxidized and reduced when a reaction does happen. So as you can see on table J, the elements at the top are labeled as being most active and the ones at the bottom are said to be least active. So this means the metals up top are the most likely to do what metals tend to do, which is lose electrons by oxidation to form positive ions. And on the right-hand column, the nonmetals up top are most likely to do what nonmetals do, which is gain electrons by reduction to form negative ions. Now, metals tend to be oxidized if they react with nonmetals, but what if two metals react, which we've seen a couple times now? They can't both be oxidized. If we react two metals with each other, one has to be oxidized and one has to be reduced. So the one that's higher listed on table J wins out and gets oxidized, and the other metal, the one that's listed lower on table J, gets reduced. For nonmetals, same kind of thing. If two nonmetals react, they both can't be reduced, so one has to be reduced, one gets to be oxidized. The nonmetal listed higher will win out and get to be reduced, while the nonmetal listed lower will do the other job and get oxidized. In the past, we've seen how a single replacement reaction will happen if the element by itself is listed higher on table J than the element in the compound that's replacing. Same thing here, we'll look at it a little bit in terms of redox reactions. So in this case, an uncharged element will react with charged ions if it's listed higher on table J than the element in the compound that's replacing. Let's pay attention particularly to these three elements: potassium K, calcium Ca, and sodium Na. Since neutral calcium is listed higher than the charged element sodium, it will react with the sodium to do a redox reaction. But since neutral calcium is not higher on table J than the charged element potassium, that reaction will not happen. And same thing down here. Since calcium is higher than sodium, it single replaces sodium in this reaction with the salt, but calcium will not kick potassium out of its molecule, since K is higher on table J than Ca is. Quick reminder of what this table shows us before we move on. It says which metal has the greatest potential to be oxidized. Remember, metals like to be oxidized. They typically do get oxidized. So when we look at metals and we see the most active metals are on top, that means the ones that are most likely to be oxidized are the ones up top. So which metal has the greatest potential to be oxidized? That's going to be lithium right all the way up top. And the least one that will be oxidized, or least likely to be oxidized, is gold all the way at the bottom, which is good because these guys right here, copper, silver, gold, those tend to be pretty expensive things. If they're going to react every time we put them outside or near other elements, that's really not going to be worth our money a lot of the time. Next question says, which nonmetal has the greatest potential to be reduced? And remember, nonmetals tend to be reduced. They prefer to be reduced by gaining electrons and getting more negative charges. So the one with the greatest potential to be reduced is the one that up here is most active, which we can see right here is fluorine. Big surprise. Fluorine is going to be most active, most likely to be reduced, and the one with the least likelihood of being reduced is this guy at the bottom right here, I2. So next example where it says which is more reactive, rubidium or cobalt, just see which is higher on the chart. The higher one will be most likely to be oxidized, the lower one will be more likely to be reduced. But in this case, we're just comparing them. Rubidium versus cobalt. Rubidium is right here all the way at the top. Cobalt is pretty far down, so rubidium is going to be the most reactive one just because it's higher up here with the active things. And then I versus F, we can see right here, fluorine's our winner up top, big surprise again there, and iodine's down here. So fluorine is the most reactive of these choices right there. Now we get to actually compare elements that are similar to each other. Remember, when metals react with each other, one of them has to be oxidized, one has to be reduced. They can't both be oxidized. So we just want to see which one's listed higher. That's the one that'll win out over the other one and get oxidized, and the lower listed one will be reduced. So if we're comparing calcium and tin, I'm going to look at my list right here, and on table J, calcium's right there. Tin is very much near the bottom right here. Calcium's listed higher. That's the one that'll be oxidized, and tin is the one that'll be reduced. Next example, magnesium and potassium. Potassium's all the way up here. Magnesium is a little bit farther down. So potassium will be the one that's listed higher and gets oxidized. Magnesium will be the one in that reaction that'll have to be reduced. Next example, titanium and gold. Titanium is right here. Gold is again all the way at the bottom. So titanium will be oxidized, gold gets reduced. Last example is kind of a puzzle here. So I'm just going to erase these ones over here so we can actually check out our chart again. This one says some metal X will react with ions of Cr, Ni, and Au. So remember, if metal X, it doesn't say it's got a charge, it'll react with ions. If a metal is going to react with something that has a charge, it has to be higher than those things that have charges. Which means if it's going to react with Cr, Ni, and Au, it has to be higher on our chart than Cr, Ni, and Au. Au is all the way at the bottom, doesn't really help us much. Ni is right here, so it has to be higher than that. And Cr is right here, so it has to be higher than that. So now we know we're somewhere above Cr on our chart. It says it will not react with ions of rubidium, aluminum, or sodium. That means it has to be lower on the chart than Rb, Al, and Na. So Rb is up here, has to be lower than that. Na is right here, has to be lower than that. And Al is right here, has to be lower than that. So we're looking for some element lower than Al, but higher than Cr. That means it could be either titanium, manganese, or zinc. We don't know which one, but it's one of those three options. In this slide, we're just kind of proofreading these reactions and seeing will they actually happen. We're going to be skeptical here and doubt what's going to happen or not. So we have to assign some oxidation numbers, see how the reaction claims it will work, and then use our chart to see will it actually work like that. We look at this example right here. Sodium by itself is 0. Rubidium over here by itself is 0. In the compound, fluorine has to be -1, and we want the whole thing to add up to 0, so rubidium is going to be +1. Right here, we know sodium is always +1, fluorine is always -1. Now we can actually look at our reaction. It has sodium going from 0 to +1, so sodium will be the one that gets oxidized in this reaction. I see fluorine on either side has a -1, so that's our spectator ion, and rubidium going from +1 to a 0, so that would be the element that gets reduced. We've done this a bunch, so we should hopefully have not really a lot of trouble doing that. This is what it looks like is going on, but would that be a realistic reaction? For that, we check table J. And if we look at it, sodium would have to be higher up on table J than Rb for this reaction to take place as listed. Rb is all the way up here, sodium's down here. Because Rb is the metal that's listed higher, Rb should be the thing that gets oxidized. And sodium, because it's lower, should be the thing that gets reduced. So as this reaction is listed right here, this would not take place like this. These reactions would not happen. Sodium, because it's listed lower, would not be able to replace Rb and kick it out of this molecule. So that wouldn't make any sense. Next example, same thing. Sodium with a 0, H with a 0. Na with a +1, F with a -1, F also with a -1 over here, H with a +1. Let's compare here. Sodium going from 0 to +1, that's oxidation. Fluorine stays as -1 on each side, that's our spectator ion. And H going from +1 to 0, H is the one that gets reduced. That means for this reaction to take place, sodium being oxidized, H being reduced, sodium would have to be listed higher on table J than H. Sodium is right here. Hydrogen's all the way down here, so this one looks pretty good. This one would happen like this. We could expect this reaction to take place as listed. On the bottom, barium with a 0, fluorine with a -1. Altogether, these three fluorines are -3. Aluminum is +3. Aluminum over here with a 0 charge, fluorine with a -1. Altogether, it's -2. So this barium right here would have to be a +2. Barium goes from a 0 to a +2, so barium is the one that's oxidized. Fluorine's -1 on each side, it's the spectator ion. Aluminum going from a +3 to a 0, aluminum would be the one that's reduced. For this reaction to take place as listed, barium would have to be higher up on table J than aluminum. Let's see if it is. I see barium right here near the top. Aluminum is kind of in the middle. Aluminum's listed higher, barium's listed higher, so barium is the one that should be oxidized. So once again, this reaction looks pretty good. We could expect that to happen. All right, one more example like this, and this is going to be a lot like the thing we do in class tomorrow. Then I really need to go to sleep. So for this, we want to see which reaction is most likely to happen. Either copper +2 reacting with Al0 to make copper 0 and Al +3, or copper 0 and Al +3 reacting to make copper +2 and Al0. And for this, we need to go to table J and just first see which is higher, Cu or Al. That'll tell us what we should expect to see. And looking at my reference table, I'm just going to pull this up on the other page here. I'm going to look at the reference table, and I see Al is roughly in the middle of the table with copper all the way at the bottom. So Al is higher. Al really should be the one that gets oxidized, and copper really should be the one that gets reduced. We're going to now see what actually happens here and see which reaction is most likely to happen. So copper has a +2 oxidation number. Al, 1 element by itself, no charge, is 0. Copper right here, 1 element by itself, no charge, that's 0. Al has a +3 charge, so we give it a +3 charge. Copper by itself, 0. Al by itself, 0. Aluminum +3, we write +3. Copper +2, we write +2. Let's look at how these things changed. Copper's going from a +2 to a 0. That charge went down, so copper right here is being reduced. Al went from 0 to +3. Its charge goes up, so aluminum is being oxidized. On the right-hand example, copper goes from a 0 to a +2, so it's being oxidized. Its charge goes up. And aluminum goes from +3 to a 0, so its charge goes down. It's being reduced. Back to table J. What did we expect to happen? Table J said that since aluminum is listed higher, aluminum should be the one that's oxidized, and copper should have to be the one that's reduced. So which of these examples shows aluminum being oxidized? That's the one right here on the left. This is the one that should happen because aluminum's higher, it's being oxidized, copper is lower, it gets reduced. This combination right here with copper being oxidized will not happen because copper is not listed higher than aluminum, so it's not going to take place. Go finish your form, come to me with any questions, and be ready to sing tomorrow.